Hello and welcome to our short introduction of reliability engineering and management. In this video, we'll take a closer look at the principles and practices that help to develop reliable products. Whether you are an engineer or a manager or simply interested in the topic, we aim to provide you an overview of how to design and manage product reliability. So, enjoy the video. This video has the following contents. First, why we need reliability engineering and management. Second, some basic definitions and terms. Third, the failure model, which is a central model in reliability engineering. Fourth, how to design reliability into products. Fifth, the process of reliability and engineering and management, which is a part of the overall risk management. After this learning unit, you should basically understand the concept of reliability engineering, and you should get to know the basic terms, and you got an insight into the local concept of reliability and the design for reliability approach. And you should understand how reliability engineering and management is anchored in a development project. So the first question is, why do we need reliability engineering and reliability management? Almost all products are subject to ever-increasing cost pressure and ever shorter time to market. We usually deal with a wide variety of suppliers, and we want to be successful on global markets where we sell our product to, where we have to deal with a wide range of loads for our product. Many of them we just do not know. For reasons of efficiency, we realize our products with modular architectures in standard components. We have to achieve ramp-ups in a short time. Therefore, we cannot afford recursions and delays in our product development process. Over time, our products are becoming increasingly complex, but customers still have at least the same quality requirements as for our earlier products, which were less complex. This increases the quality requirements for every single function and every component. Reliability engineering enables us to achieve high quality and customer satisfaction even under great cost and time pressure. We can therefore develop without safety margins or with less safety margins in design and still keep quality cost at a competitive level. With the help of the model-based approach and design standards, we can further optimize efficiency and time to market. Let's take an example. When you press the button of your coffee machine in the morning, you just wanted to dispense your favorite coffee, don't you? If you only get cold brew instead, you're really annoyed. Drops or puddles of water, strange noises, cracks in the housing, and loose buttons can also annoy us as customers. And from the perspective of the manufacturer, if this occurs during the warranty period, we already incur high costs. But even worse are poor ratings. They can even lead to falling sales figures. In the worst case, that can catapult a manufacturer out of the market. Reliability engineering and management are therefore a necessity in order to remain successful on the market. But the question is how to do this. Before we go any further, we should classify the concept of reliability. In the quality model of technical systems that contain hardware and software functions, the major quality attribute is dependability. Dependability covers reliability, availability, maintainability and repairability, as well as product safety and data and information security. Taken together, these are the so-called RAMSS attributes. By reliability, we mean the durability of components and the reliability of systems. On this slide, you see the definition of reliability. What does it mean? Reliability means that a function is executed under specified conditions within a defined time interval. The time interval is usually the specified service life, for example, 10 years. If the function is not carried out as intended, it's a failure. Since we are talking about the durability of components here, we can also speak of a component failure. Failure events are random, and we cannot predict if and when a failure will occur. Reliability is therefore subject to a stochastic process and can be expressed as the probability to survive in a specific time interval. Reliability cannot be directly measured for an individual design or component. So back to our coffee machine. The coffee machine contains a lot of plastic seals. If they lose their sealing function, water or coffee drips out. That's a failure. We ask now what caused the failure of the seal. One reason is that aging processes in the seal and ongoing mechanical loads lead to a loss of elasticity and cracks. In general, we speak of these processes of damage mechanisms that lead to failure. Typical damage mechanisms are wear, degradation, rupture cracking, fatigue cracking, creep, or corrosion. Now it's the point to introduce you the local failure model of reliability engineering. First, we look on the loads. Several load types act on the seal of our coffee machine. Static and dynamic forces act on the seal during operation and also when the machine is in an idle state. They are caused by the internal pressure of the liquid in operation or just by forces resulting from the assembly in the pipes. It is also in contact with air, water, coffee, and descaling agents. These media cause chemical changes in the seal material. Chemical reactions are usually accelerated by higher temperatures. These additional loads stress the seal additionally and can ultimately cause a crack. The sealing material has a certain resistance to stress caused by the loads, but only up to a certain limit. We call this limit the fracture strength. A crack occurs only if the strength of the plastic is exceeded. In the case of the seal, this could be a fatigue crack due to the cyclic pressure change. This could happen in conjunction with degradation of the material under the influence of media and temperature. Let's summarize. Failure of parts are caused by damage mechanisms. Each damage mechanism is triggered by a certain type of loads. Loads are environmental and operating conditions such as forces, pressures, temperatures, media, and so on. Loads cause local stresses on parts, often in a combination. Parts have a certain strength to failure. Failure occurs when and where the stress exceeds the strength. Now we need to look at this statistically. As a manufacturer, we produce and assemble lots of parts, sometimes millions of parts. The properties of the parts are subject to fluctuations, which are mainly caused by scattering production processes. Stress acts on components influencing its performance and durability. Stress as well scatters, for example, due to varying operational conditions. Not every user acts and operates our product the same way as another one. Failure occurs locally, exactly if the condition stress is bigger than strength is fulfilled. In this diagram, it's indicated in the overlap area of the two distribution functions. Mathematically, it's a bit more sophisticated, but for the moment we can simplify accordingly. So the next point is, how can we make use of that knowledge in a design for reliability approach? How can we increase reliability? The concept is called design for reliability or reliability by design and can be illustrated using again the two distribution functions of stress and strength. First, we can reduce the loads, so shift the mean of the distribution function of the loads and stress to a minimum value, a shift to the left by design measures. Sometimes it's sufficient only to reduce the spread of the loads by limiting tolerance ranges. Another option is on the right side of the distribution functions, the strength. Increase the resistance of the material, increase the mean of the strength by using better material. Or again, just reduce the spread of the strength by limiting the tolerance ranges of the production processes. As a result of these actions, the overlap area of the stress and strength functions becomes smaller. That means we reduce the probability to fail and increase the reliability. Again, let's take our seal of the coffee machine and look how design for reliability measures could work. In principle, we have the following options for improving or increasing the reliability. Firstly, we can reduce the loads by reducing the pressure, for example, by increasing the pipe diameter. We can also limit the tolerance range of the pipe diameter. Limiting the maximum temperature could be another option, or ruling out the use of critical chemicals. Some of these measures are only theoretical because there are constraints by other requirements of the system. A further option is to increase the chord diameter of the seal. If we turn now to the strength, we can improve the sealing material, choose a sealing material with a higher strength. If we investigate all the different measures and weigh them up in the early concept phase, we can choose the best strategy. Best is to do it in an early project phase because there are minimum constraints in this phase, so we can really choose the most effective and the most cost-effective strategy to be implemented. So now at the end, let's turn to the process view, the reliability management process. The reliability management process is part of the overall risk management process. It starts by defining the reliability targets. What level of reliability should be achieved in the product? Then we design a concept or an architecture, and based on this architecture we assess the reliability risks. Here we use methods like the FMEA, failure mode and effects analysis. Also the so-called focus analysis is very suitable and very straightforward, or we apply design review based on failure mode, in short DRBFM, There are several ways to straightforward identify and prioritize reliability risks. So the general approach to reduce or exclude uh, reliability risks is the design for reliability approach, which you already have seen in the previous chapters. Ideally, field data supplements the process and answers the question if the reliability targets are actually valid and fulfilled. The entire process might be repeated several times during a development project. Let's summarize all. Reliability engineering and management aims to achieve product reliability at minimum product cost and shortest time to market. The application in early project phases enables the development of reliability as a product characteristic. With reliable products, we will save money, satisfy our customers, increase our sales, and even extend our markets. Thank you for listening. Please leave us a feedback about what you liked and what you might have missed. We would also be happy to hear from your experiences in your projects too. If you want to learn more, if you want to apply the concept quantitatively to your components in your projects, we invite you to our course Reliability Basics. Hopefully, see you soon. Goodbye.